Okay, so what we're going to do today is we're going to solve an AP Physics free response problem from 2006 that involves some sort of linearizing technique. Great. So I'd encourage you to go ahead and try this problem completely yourself all the way through, and then you can check the video to check your answer. Great. So in this problem, a student wishing to determine experimentally the acceleration g due to gravity has an apparatus that holds a small steel sphere above a recording plate as shown above. When the sphere is released, a timer automatically begins recording the time of fall. The timer automatically stops when the sphere strikes the recording plate. The student measures the time of fall for different values of the distance d shown above and records the data in the table below. These data points are also plotted on the graph. Great, so I have my good old table, and then let me scroll down for my graph. Okay, so our first part, for A, on the grid above, sketch a smooth curve that represents the student's data. Okay, well, they're already giving me hints, and I know it probably should be a smooth curve, so I'm going to go ahead and sketch a smooth curve. Cool. So it definitely does not look, just out of observation, it doesn't look linear at all. Probably quadratic, but not 100% sure right now. Cool, so let's go ahead and go on to part B. Time t to produce a second graph from which acceleration g due to gravity can be determined. For B, if only the variables d and t are used, what quantities should the student graph in order to produce a linear relationship between quantities? Cool. So first thing, if it says linear relationship, I know I'm probably going to be linearizing in this problem. Cool. Okay, so first thing I'm going to go ahead and do is I'm going to go ahead and try to figure out some equation that represents the relationship between d and t in this data. So I know something was falling through the air. We're trying to find acceleration to gravity. It's a constant acceleration. I'm going to go ahead and set up my constant acceleration equations. Vi, df, a, delta x, and delta t. Great. So I know, okay, the student drops object from rest, so vi is 0. I don't know vf, it'll hit the ground at some speed. Acceleration, this whole lab, I'm trying to find the acceleration. That's the goal. I want to find what the value of g is. So I'm going to put question mark for acceleration. Displacement is distance d, they call it capital D. And delta t is just t, they call it t. Great. So I'm going to go ahead and pick a good old constant acceleration equation that includes all these variables. And I'm going to choose delta x is vi delta t plus 1/2 a delta t squared. Great. So delta x in this case is d, vi is 0 times delta t plus 1/2 acceleration I don't know, and this is just going to be t squared. Great. So the first term disappears. d is just 1/2 a t squared. Cool. So that equation right here, and I'll go ahead and box this, that will represent a relationship between distance and t. Cool. I notice there's a t squared in there. I notice there's a d. Cool. Let's figure out now what quantities we need to graph. So again, I always compare this equation that represents the relationship between the data to a linear form, which is y equals mx plus c. Cool. So in this case, it looks like d is like y, and then b in this case, that's definitely looks like 0 right there. So I'll go ahead, 0 is like b. So now the x variable, that is like your independent variable. So what else up here is like something that's changing a variable? That's going to be t, but it's squared. So that is going to be t squared. So x is going to be t squared. And then that's just going to leave us, our slope, or m, is going to be 1/2 a. So d is y, 1/2 a is m, excuse me, and then t squared is x. Great. So it looks like I'm going to need to go ahead and graph. I'm going to need to graph d versus t squared in order to produce a linear relationship. Okay, so since I know that I'm going to need to plot d versus t squared, I'm going to go ahead and just get a head start and do some figuring out. So I know, let me just rewrite my table. So I know times seconds, let's see, and d is what, meters? Great. So I know at 0.14, the distance is 0.1, And then I'm just going to write down the other ones. Okay, so again, this table, t versus d, that's just from the data that it gave us in the problem. I just rewrote it here. Cool. So now we're going to need to linearize it. We're going to need to graph d versus t squared. So we already have d. We're okay on d. D is just d right here. Cool. Same thing as d over here. Great. Now, though, we need to graph t squared. So I'm going to go ahead and make another column to try to get t squared. And so I know the units of t squared, that'll just be second squared. So to get t squared, I just need to take each of my time bit values and square them. So the first one is going to be 0.14 squared, which is just what? Plug in the old calculator, 0.0146. Great. Next one is 0.32 squared, which is 0.1024, and then I just can keep on going. 0.46 squared is 0.2116. 0.59 squared is 0.3481. 0.63 squared is 0.3969. Great. So now I have all my data. And again, t squared, that is going to be this whole thing right there. Okay, so now for part C. On the grid below, we'll plot the data points for the quantities we have identified on part B and sketch the best fit, straight line fit to the points. Label your axes and show the scale that you have chosen for the graph. Cool. So we just decided that we're going to go ahead and graph D, which is in meters, versus t squared, which is going to be second squared. Great. So I'm going to go ahead, I'm going to just say this is 0, this is 0, D, I'm going to count by, I think 0.5 sounds nice, so that's 1.0. What is that? 1.5, 2, and 2.5. T squared, I'm just going to choose a nice, easy, let's see, yeah, I'll do 0.1. So this is 0.1, this is 0.2, this is 0.3, this is 0.4. Cool. I probably shouldn't extend the graph a little bit, but I just really like these axis labels that I have, or scales that I have. Great. So now let's go ahead and go up to our data. So our first data point, let me just scroll up, is, okay, so this is just going to be our first data point, is 0.1 for D and 0.0146 for T squared. So let's scroll back down to that. And again, because we're graphing D versus T squared. So we'll do 0 point something in here, and then something in here. Cool. Our next data point, D is right about 0.5, and T squared is just a tiny bit over 1. So it's going to be about right here. Cool. Next data point, we have D, oh, excuse me, that disappeared. Cool. Next data point, we have D is about 1, and then T is just a little bit above 0.2, so right about here, and I'll just go ahead and graph the rest. Cool, so I just went ahead and graphed the last 2 data points too. Cool, good thing is, it looks pretty darn linear, which is what he wanted it to be. Cool. Now let's go ahead and sketch the best straight fit line to the points. I'm going to go ahead and just draw a best fit line, and again, always use a ruler, or if you're on your computer, use Excel or some other program to find the best fit line. Cool. And again, for your best fit line, you want about the same number of points above and below your best fit line. Okay, so now let's go ahead and look at part D. So part D says, using the slope of your graph in part C, calculate the acceleration g due to gravity in this experiment. Okay, so first thing I do, the problem says using the slope. Anytime a problem says using the slope, guess what you're going to have to do? You're going to have to find the good old slope. So always when you're finding the slope, show your work for it. The slope is what? Rise over run. And again, when you find the slope, you always need to choose 2 points on your best fit line. They can be your actual data points, they can be other things, whatever. I'm going to pick, oh, the origin looks nice, and this point looks nice. That looks like that's about right on the corner. So rise in this case is 1.5 minus 0 over run is 0.3 minus 0. Cool. Go ahead and do some math. Cool. So let's see, 1.5 over 0.3 is just going to be 5. And I should put in units too. The rise is meters, and then the run is second squared. So that is the slope. We're going to come to that more in just a second. Great. So now I'm going to give myself a little more space to work with. So again, the goal of this is to calculate the acceleration due to gravity in this experiment. So again, our original equation was a equals 1/2 at squared. And again, our linear form of equations is y equals mx plus b. So again, we know b is like y, x is like t squared. So the slope m is like 1/2 x. Cool, let's write that down. So slope equals 1/2 a. Cool. We found the slope. We just did some good old graphing. We found the slope to be 5 equals 1/2 a. So we do some math. So cool. Slope is 10 meters per second squared, which is a. So we just have found the acceleration due to gravity is about 10 meters per second squared, which, cool thing is, that's about what it should be. Cool. So let's go ahead and just look at part E. So state one way in which a student can improve the accuracy of the results of an experiment. If the experiment were to be performed again. Explain why this would improve the accuracy. Cool. So one good thing that's always great to do is do multiple trials for each value of d. And doing more trials, and then again you take the average to get each value of d. This just reduces personal and random error in the experiment. Cool, and we are all done with this good old AP Physics free response problem. Thanks for watching.